Today we're learning about heat transfer. Is a thermochromatic screen, and it uses color to represent the temperature of any object it touches. Mercer, you are going to put your hand on our thermochromatic screen for 25 seconds. Ready, go. 1, 2, 24, 25. Now lift it straight on. Subscribe! Look at that. I'm gonna try his fingerprints.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25.
So it looks like on this, the very hottest parts are blue, then green, then yellow, then red.
So it's basically the opposite of what usually. There was hardly any blue. There's only like a tiny bit in the center, but there was lots of green. And then as it gets cool, as it cools down, it slowly all fades to red and then goes away.
Now we're going to see how warm your breath is, Sterling. So you're gonna get that straw out. And then you are going to blow. You're gonna get pretty close. They want you to get about 1 to 2 centimeters away from the thermochromatic screen. And you're gonna blow your breath. Ready, go.
1, 2.
Oh, you don't have to count. He's just gonna blow to see how warm his breath is. Wow, look at that.
It got actually a lot of blue.
Okay, do it
Try again.
Look at all that blue. But it really fades away fast. There's just so much blue.
Beckham's gonna try now and see how warm his breath is. Did you guys notice happens after you make either your fingerprints or handprints, or if you blew warm air on it? Does it stay for very long?
No, because the heat doesn't last.
That's right. Any warm object gradually loses its heat to the cooler environment or objects that it touches, right? So if you leave two objects in contact for a long time, they eventually will become the same temperature, right? This is basically how thermometers work. The passing of heat from a warm object, like your hand or your breath, to a cold one is called heat transfer. Here's a little color map that shows what temperature each color is. So Sterling put his whole palm on there. And so of course when it's the very hottest, it's blue. It's purple when it's the very hottest. Then it turns into green, then an orange, then a red.
I think you got a
And
little
it's
bit of
back to
purple
black.
in there, but then mostly blue and now it's green. And then
Yeah, I got
red.
a little bit of purple in there.
It's very cool.
Going one more time. Everybody crush my hands.
It'd be interesting if you tried to use some friction, rub your hands together, and then put it on there and see how hot you can get it.
But we have to find
We'll
the
do that
average of what color we usually get, which I think is 30.
Okay, go ahead.
Okay.
Let's see it.
Take it.
Whoa!
Okay,
Now, rub my hands together. So then when we try it again, my hands will be hotter.
Why are we doing it?
I don't know.
You're using friction to create some heat.
You can feel the heat on your hand as you do this.
Yeah. No one's gone. Okay. Man.
Almost a few more seconds. Just burns will go faster now.
Ready, go.
I was crushing my hands.
That's what we're supposed to do. No, this is gonna
Push
be
harder. Hearts can't do.
Maybe it'll still be black.
Yeah,
Let's see if we can get it up. So So if you get it up to the purple, that means it's 93 degrees Fahrenheit.
Okay, let's go now.
Okay, go. Let's see what we got.
Oh,
I don't think we got any purple, but
no,
I've noticed that.
see, that's kind of purpley bluish. And you see the scale, that's like a purple.
Whoa. I've noticed that your palm is more hot than your finger.
Why do you think that is?
It's because it's close to your butt.
Maybe because, but also probably because that's where when I was
Try to foot
that
that.
was where the most friction happened.
So Beckham's got some boiling hot water in this mug, and he is going to drop a little piece of cotton in there.
Do that.
Okay, now he's gonna put it in there for 3 seconds. 1, 2, 3. He's gonna pull it out. He's gonna put it in there. And then we are gonna put this on top. Let's see what happens.
Oh man,
Yeah, it's glowing.
it's purple, guys.
That's a dark
that middle
purple.
turn
Wait,
purple?
Can we go back to the one?
That is really deep purple.
Yeah, that's
So
like,
that was just a little piece of
that's
cotton
like 33.
absorbed into some hot water. And then when we put this up on top of it, you can see how hot that is.
What if we put it in there longer?
And what's like the difference between when you put your fingerprint on there and then you take your fingerprint off? It fades pretty quickly. What's happening right now?
I know
not
there's
fading.
not a lot of air, cooler air coming in to cool it off.
Okay.
So that's why it's staying hotter for longer.
And I think that's like a
It's very cool.
32 on the
So, and you can clearly see as well, where is the very hottest?
In the
middle.
center.
In the center, and then what happens as it goes outward?
It starts to fall downward and nothing.
Okay, so Archer, according to this this temperature gauge,
It's about 30.
about what temperature?
Like around 33.
33 degrees Fahrenheit, which we decided was 93 degrees. I mean, 33 degrees Celsius, which is 93 degrees Fahrenheit. And then how about the cooler temperatures?
They're like 75.
Yeah.
They're still a little bit hotter because when you put this in,
Pull it out.
almost.
Just squeeze it. Keep squeezing it.
Keep squeezing.
Put it right
Put
in there.
Okay.
It got a
Ooh,
bunch
it's
right
getting
there
hot.
for a second.
Starting to grow. We can see it's around 32, 33 maybe.
1, 2, 3, 5, 7, 8.
So everything is made up of tiny particles called molecules. Yet the same object can be both hot and cold. What does this mean for its molecules? They are constantly moving at different speeds. Heating an object accelerates its molecules and increases the object's temperature. In solid objects, the molecules are tightly held in place, and when heated, they merely begin to vibrate faster, until the point that they vibrate so intensely they begin to break the bonds holding them in place. When the objects of a solid object when the molecules of a solid object begin to vibrate really fast, the object will gradually transition from its solid to its liquid form. In other words, it will melt. Molecules in liquids move more freely. Leave a drop of water on a table and it dries up over time. However, its molecules do not disappear but become vapor or gaseous water and drift away, mixing with the air. The process of converting a liquid into a gas is called evaporation. During evaporation, the fastest moving or hottest molecules gradually abandon the liquid for the air. Hot water has a lot of fast molecules that are eager to leave the liquid. Once they do, mostly slow molecules remain. That's why the temperature of the remaining liquid lowers. And the thermochromatic screen reflects this cooling process.
Yeah, someone did it like in a punch in one area and it was really like blackish.
Now we're going to perform an experiment to see which is faster. Do you think it is faster to heat or cool an object? Beckham, what's your hypothesis? Do you think it's faster to heat an object or to cool an object? Mercer, do you think it's faster to heat an object or cool an object?
Cool.
Sterling?
Cool, because I think, and it's harder to get stuff hot, I think.
Archer?
Yeah, cool.
We have two rods here that are the same size. This rod is made of aluminum, and this is a heat pipe. And so we are going to get some hot and cold, and then we are going to discover which is faster, heating or cooling an object. Go ahead and put each rod in by pushing it in, and then you'll put this on top in that little hole. Okay. Okay, now you're gonna go ahead and stick this down so it covers both of the rods and push it down. Okay. Now you're gonna put some hot water in this one. Here, let's put the sticker on. And then just fill it about halfway up, okay? Now we have a bag of hot water, and we are going to set it on our two rods, and we are going to watch and see how quickly the rods heat up. And you're also going to notice which one heats up faster. So you need to observe very carefully. So here goes our hot water.
See how hot it gets. Nothing really so far.
Oh, there's a little bit right there.
Oh, I'm watching mine.
So this is,
Oh, there's a
the
little
copper is definitely going faster.
in the aluminum.
Look at the, you can see a little bit right here though.
Yeah.
Let's look. You can kind of see like a
There's a blue.
bluish.
There's a blue stripe on the copper one. There's a little bit of blue on the aluminum one, but it hasn't made it to the end like the copper one has.
Right.
I think that
It's almost there.
that this one has more green than blue.
If one object heats another only at their point of contact, how do large or long objects end up heating up entirely? At the point of contact, the fast molecules of the warm object collide with the slow molecules on the surface of the cold object, pushing them to move faster. Next, these faster molecules in the cold object collide with the adjacent molecules in the deeper layer of the cold material, pushing the slow molecules there to also move faster. Thus, the temperature of the object gradually rises as the speed of its molecules increases. When heating in one place, an object gradually becomes the same temperature throughout its volume. An object's ability to spread heat or cold through itself is called thermal conductivity. The rate at which heat or cold is transferred along an object depends mainly on the material. Saw how quickly those heated up. Do you still stick by your hypothesis that it's going to cool down even faster? Beckham's changing, Archer's changing. Sterling and Mercer, you're gonna stick with it? Okay, here we go.
Take a look.
Okay, so Sterling is going to start us off by putting some drops of water in the center of our box. Go ahead.
Okay.
In the middle?
Yeah.
Mhm.
Okay.
Okay, now go ahead and put a piece of ice on top of the salt. On top of the salt, please.
On top.
Good. And now we're gonna wait 2 minutes. Okay, go ahead, Beckham.
Stuck.
Is it frozen on there?
Yeah.